Okay, so let's talk about graphs of functions of two or more variables. Now, of course, graphs are a way for us to visualize the behavior of a function, the relationship between the inputs and the output. Okay, and again, typically the output is z, and that is what is that? That's the vertical axis, right? So that's going to be your output. Your inputs are x and y. Okay, so and of course, that's why it's important for us to know the domain, because that tells us a restriction on the range or the outputs. So we got a little bit of an introduction to surfaces. We looked at quadric surfaces at in chapter 12, I think, right? But the surfaces that we looked at we just looked at 6 types of surfaces. And so you can of course have many different, you can have functions that aren't surfaces, okay? So if, however, you were able to write it z equals f of xy, then that's called a surface, okay? So we can visualize the graph of a surface by plotting it like this. So you go to your input, which would be xy, and then based on z, which is the output, you determine how high or how low. If your z value, right, if the output is negative, then the point is below the xy plane. Okay. Now let's look. If we were to sketch the graph of this function here, this is f of xy equals 6 minus 3x minus 2y. Now, if we first we rewrite it like this, z equals 6 minus 3x minus 2y, then we can see that just by rearranging it, we get the equation of a plane. Right? So it's a plane and normal to the plane. So just looking at it, this plane goes through the point 1, 1, 1, right? Because 3 times 1 plus 2 times 1 plus 1 is equal to 6. So this contains the point 1, 1, 1, and it has a normal vector of 3, 2, 1 is normal to the plane, right? But so now one way to sketch the plane is to first find the intercepts. So we'll have 3 intercepts. We'll have the x-intercept, the y-intercept, and the z-intercept. So to get the x-intercept, you set y equal to 0 and z equal to 0. So now in this equation, if we set y equal to 0 and z equal to 0, what do we get? So it's here. So if we set y equal to 0 and z equal to 0, then that means that, oh, x has to be equal to 2. Does that make sense? So we've got 2, 0, 0 as our x-intercepts. So if I can just sketch it here, that means 1, 2. So this point here, 2, 0, 0 is on our plane. Okay? And now we do something similar. We get the y-intercept by setting x equal to 0 and z equal to 0. Now, y is going to be equal to 3, and so 0, 3, 0. So that means go out 1, 2, 3. Okay, so the y-intercept is there. And then the last thing we do is find the z-intercept, which would be just z equals 6. So we'd have 1, 2, 3, 4, 5, 6. Okay, and so now that we know the 3 intercepts, there's only one plane that goes through all 3 of those points, and that's a way for us to sketch the graph of the plane. Okay? So this portion here, if you form that triangle, that's just telling you the part of the graph that's in the first octant. Okay? Now, in general, anytime you have a function like this is called a linear function, right? Because it depends on x linearly and it depends on y linearly. Okay? And the equation, so when you sketch a linear function in 3D, you get a plane. Okay? If you sketch a linear function in 2D, you get a line. Okay, so a linear function in 3D has the equation z equals ax plus by plus c. And a linear function in 2D has the equation y equals mx plus b, right? Or you could even write it ax plus b. So you see how there's a similarity between the equations, right? So they're both linear, but in 2D, the graph of this linear function is a line, but in 3D, the graph of this linear function is a plane. Okay? All right. So linear functions, of course, play a central role in multivariable calculus because imagine if we've got a surface, right? In order to describe, say, tangent, we don't talk about the tangent line because you could have several tangent lines, right? Instead, we talk about the tangent plane. So we will be finding equations of the tangent plane to the surface at the point. Okay. So now let's go through here and sketch the graph of g of xy equals the square root of 9 minus x squared minus y squared. So the thing to notice in order to graph this is to say, hey, look, if we square both sides, we get z squared minus equals 9 minus x squared minus y squared, right? And now if we rearrange, then we would get z squared plus y squared plus x squared equals 9. And we know that this is the equation of a sphere, center at the origin, and a radius of 3. Okay. Now the only modification we need to make is the following. We used z equals plus square root, so we just need the top half of the sphere, right? So if, for instance, if we had z equals negative square root 9 minus x squared minus y squared, then we would just be using the bottom half, right, of that sphere. But since we're doing the plus, we'll have just the top hemisphere. So that's a crappy looking hemisphere, but hopefully you get the idea. Okay. Yeah, here's a better picture. So for instance, if we were to graph this with Mathematica, we would do contour plot, 3D, okay? And we could have x squared plus y squared plus z squared equals 9, x squared plus y squared plus z squared, and then 2 equals sign, 9, comma, and then x, you could make it from, say, negative 4 to 4, y to be negative 4, 4. And now for z, because we just want the top half, we could put z to be from 0 to 4. Okay? Or, alternatively, if you were to change your function and say, hey, no, I actually want to put in z equals square root, right? And then 9 minus x squared minus y squared. Then you don't have to worry about restricting the domain because automatically Mathematica is going to know that it can't take the square root. Right, it's going to know that the square root is always going to be non-negative, so it's not going to plot any negative z values. Okay. So this is similar to the case with a circle in 2D. In order to have a function, right? In order to have a function, we have to have exactly one output for every input, right? So if we were to have the sphere, then we need to say for every point x, y, there can't be two outputs. See how there's like one in the bottom half and one in the top half? You can't have that. So in order to turn this into a function, you do have to split it up into plus and minus square root. Okay. And of course, we know how to use a computer to draw this graph, right? Then notice in Mathematica, you would just put contour, plot, 3D, and you could just put P, not capital P, it'd have to be a lowercase p. So you could say P equals, and a double equals 1.01, and then put a lowercase l to the 0.75, and then times k to the 0.25. It's 1730. Right, and then you just give your domain for L, right, maybe negative 10, 10, and your domain for K, negative 10, 10, and your domain for P. Okay, so it looks like this is what a sketch looks like. Notice that Stuart uses Mathematica to make the pictures. So this has the box, right? And the L is here, the K is here, and the P is here. Okay. And this is something I think I didn't really mention from before, but how does Mathematica draw? How does Mathematica plot? It uses the traces. So it uses the traces and then fills in the inside of, kind of brings the traces together in a continuous way. So that's why we see these lines. These lines here are actually the traces of the function. Okay. Find the domain and range. So for the domain, x can be anything and y can be anything. So we don't have any restrictions because we're not taking the square root, we're not dividing. So the domain is going to be all reals. And for the range, well, you'll never get a negative number because 4x squared plus y squared can never be negative, right? Because y squared is non-negative and x squared is non-negative. So the range is going to be from 0 to infinity. You could get 0, which is when x and y are both equal to 0. And now to sketch a graph, we'll have z equals 4x squared plus y squared. And this is something that we actually did back in chapter 12. Okay. And the graph is a elliptic paraboloid. Okay, horizontal traces are ellipses. So if you split it like this, you'll get a bunch of ellipses, right? And then if you split it like this, if you take a vertical trace, you're going to get a parabola, which means it's like that, right? So imagine a bunch of parabolas and ellipses, and it all comes together as this elliptic paraboloid. Okay. So graphs by computers. Computer programs are readily available. They are. We know about them. We've been using them, working with them. And you can kind of see the pretty graphs here. So all of these are referenced in your textbook. But the key is that these are no longer just quadratic surfaces. You can do things with sine and cosine. Exponentials are in here. And Stuart is talking about how you can rotate. So that's one of the benefits as well, is that you can, with Mathematica, you can take the graph and rotate it. Because you're dealing with a three-dimensional image, you need to be able to look at it from the back, from the top, and all of that, right, to get different vantage points. Okay. So notice here that the x-axis is to the right, whereas here the x-axis is to the left. So you're really looking at it from different vantage points to get an idea. Okay. And the next thing we'll talk about when we come back is another method for visualizing functions, which is called level curves.